In this lecture, we'll address reductions, specifically hydrogenation and hydrogen transfer agents. Hydrogenation can be used to reduce several functional groups. These are several examples that can be reduced to these target functional groups, and in this table, these groups have been arranged according to ease of reduction. So the groups at the top of the table are easier to reduce than the groups at the bottom of the table. And now this comes in handy if you're trying to reduce selectively one group over the other in the same molecule. Now if we look at some of these reductions, we can look at the first one where an acid chloride goes to an aldehyde. This particular reduction has a name and it's called the Rosenmund reduction. And we'll look at it again later on in this slideshow. We can also reduce a nitro group or an azide to the corresponding amine. So this means that this is actually a good way of protecting amines. So we can mask amines as azides or nitro groups and then reveal them at whatever point we need it. We can also reduce alkynes, and remember for hydrogenation we are always going to go to the cis alkene. We can reduce aldehydes to the corresponding alcohols. We can reduce a cis or trans alkene to an alkane. We can also reduce ketones to alcohols. Now for all carbonyl compounds, we prefer to use group 3 hydrides. So for carbonyl compounds like ketones, aldehydes, and some of the carboxylic acid derivatives, use boron or aluminum reagents. The group 3 hydrides are a far better choice. They have much more selectivity for carbonyls over other functional groups. We can also do hydrogenolysis, so we can remove a benzyl group, for instance, to reveal the alcohol. And we can also reduce a nitrile and get a primary amine. When we're planning a hydrogenation reaction, we have some things to take into account: solvent, catalyst, pressure, and temperature. When we think about the solvent, as solvent polarity increases, the catalyst reactivity increases. So a catalyst will be more reactive in a more polar solvent like acetic acid or water than in methanol, and that's going to be more reactive than in ethyl acetate and definitely more reactive than in something nonpolar like hexanes. When we consider the catalyst itself, palladium on carbon is the most common catalyst that we use, and it's available as a 5% palladium on carbon or 10%, 15%, 20%, and so on. Now palladium on carbon is one of the more reactive ones. It's more reactive than platinum oxide, palladium hydroxide, and this combination might look familiar. That's the Lindlar catalyst combination with palladium on barium sulfate and quinoline. Usually we will have hydrogen gas at 1 atmosphere or higher pressure, and the temperature ranges from room temperature to high temperatures. Now let's look at some catalyst reactivity examples. The Rosenmund reduction and the Lindlar reduction are examples of weakened catalysts. So for instance, palladium is poisoned in these cases and has lower activity than palladium on carbon. If we look at the Rosenmund reduction, in this example we have a compound that has several functional groups that can be reduced. We've got 2 alkenes and we've got an acid chloride. When we treat it with hydrogen, 5% palladium on barium sulfate, which is our Rosenmund catalyst, and we reflux this reaction in toluene, we get selective reduction of the acid chloride to the aldehyde. There is no reduction of either alkene, and there is no further reduction of the aldehyde to the alcohol. Now contrast this reaction with a reaction where we use palladium on carbon as the catalyst. In that case, if we used palladium on carbon, both these alkenes would have reduced to the corresponding alkane. The Lindlar catalyst uses a similar approach, and the Lindlar catalyst can be palladium, barium sulfate, and quinoline, or palladium on calcium carbonate with lead acetate and quinoline. In conjunction with hydrogen gas, it reduces alkynes to the cis alkenes. However, notice that it doesn't reduce the alkenes any further. It also doesn't touch this transalkene that we already had. Now let's look at heterogeneous catalysts in alkene reduction. When we think about heterogeneous catalysts, we're thinking about catalysts that are not soluble in the solvent. So all our palladium on carbon catalysts are not soluble, and they are heterogeneous catalysts. In this example, we're looking at one of the problems during alkene reduction, and that is the possibility of isomerization. Now, this is usually a problem when you have the possibility of forming highly substituted alkenes, which you know are stable. And here, for example, we're starting with a tri-substituted alkene that we would like to reduce. We're treating it with 1 atmosphere hydrogen, platinum, and ethyl acetate. And while some of the alkene will reduce, we will also get a side product where this tri-substituted alkene has now isomerized to the more stable tetrasubstituted alkene. What's happening in this reaction is that after our transition metal coordinates to the alkene, instead of doing the hydrogen addition at that point, we have elimination to give the more substituted alkene. Note that we could just reduce this alkene and hydrogenate it until it becomes the alkane. However, at this point, we have lost the stereochemistry at this stereocenter. In hydrogenation, we have syn addition of hydrogen. That is, both hydrogen atoms are delivered from the same side of the alkene. If we look at this example, we can see that both hydrogen atoms can be delivered from the top, or both hydrogen atoms can be delivered from the bottom. In this particular example, if we have delivery from the top, we will form the cis-decalin. If we have delivery from the bottom, we will have the trans-decalin. If we look at hydrogenation, we find that the cis-decalin is favored in a 93:7 ratio, whereas if we use the Birch reduction, which undergoes a single electron transfer mechanism, so in that case we're using lithium and liquid ammonia, we almost exclusively favor the trans-decalin. In the stereochemical analysis of this reaction, we can draw the chair conformation. This is the alkene that we're interested in. We have the hydrogen and this cyclohexane coming out at us, and we have the cyclohexane with the carbonyl going at the back. And you can see from this chair conformation that due to the presence of this cyclohexane, this is our concave side and it is significantly more hindered than the other side. Now palladium is rather large, and so it's going to favor the less hindered side to bind to the alkene, and so the hydrogen is delivered from the less hindered side. Now let's look at some homogeneous catalysts. These are catalysts that are soluble in the solvent. The first example is Wilkinson's catalyst, which is rhodium that's bound to 3 triphenylphosphine molecules and 1 chloride. Wilkinson's catalyst has pretty good selectivity for electron-rich alkenes, and that's because electron-rich alkenes are better able to coordinate to rhodium. In comparison, hydrogen and palladium on carbon has poorer selectivity. Now let's look at the mechanism for this reaction. It's a fairly common cycle for most transition metals. In this case, we are starting with ligand dissociation. That is, one of the triphenylphosphine ligands is dissociating from the rhodium. Rhodium at this stage is at the rhodium +1 oxidation state. Oxidative addition of hydrogen gets it to the +3 oxidation state, and you can see that the hydrogen is now inserted. We then have coordination to the alkene, followed by migratory insertion, where the rhodium is inserting into the alkene and at the same time has delivered one of the hydrogens. Reductive elimination takes the rhodium +3 back to rhodium +1, regenerating the catalyst, and at the same time releasing our reduced alkene. In the first example, we've got an example of selective reduction of the more electron-rich alkene. So this alkene which is more electron rich, has been reduced to the corresponding alkane. And this alkene, which is electron deficient because it is in conjugation with the carbonyl, remains untouched. In the second example, we started with the alcohol that we deprotonated with potassium hydride, and then this alkoxide coordinates to the rhodium in this fashion and directs the hydrogenation from the top face because the alcohol is on the top face. So this is an example where we've got hydroxyl-directed hydrogenation. Now let's continue with homogeneous catalysts but focus on cationic catalysts. These are good for hydroxyl-directed hydrogenation. The first example is Brown's catalyst, and that is rhodium diphos. This is the structure of rhodium diphos. And this is great for allylic and homoallylic alcohols. Homoallylic is just an extra carbon than an allylic alcohol. So this is an example of a homoallylic alcohol. In this case, we've got hydrogen at high pressure with rhodium diphos and dichloromethane. The oxygen is on the top face and is going to bind to the rhodium and cause delivery of the hydrogen from the top face. And so the methyl group is now at the back. Crabtree's catalyst is an iridium-based catalyst. So iridium is just below rhodium in the periodic table. And in this case, you've got similar activity. So there's no hydrogen here. You've got similar activity to Brown's catalyst. Just for clarification, COD refers to this group, which is a cyclooctadiene, so cyclooctadiene, and CY is just the cyclohexyl groups, and this is pyridine. Now we're going to look at an example of asymmetric hydrogen transfer. There are several of these reactions. We're going to focus on just one, which is the Noyori reduction. And when we talk about hydrogen transfer agents, the one that we look at most commonly is just hydrogen. We can also use, though, formaldehyde, isopropanol, and cyclohexadiene. Now in this example, we're using hydrogen at high pressure, ruthenium acetate, S-binap, and methanol, and we're enantioselectively forming the S enantiomer from this alkene, and that gives us naproxen. The enantioselectivity of this reaction comes from this reagent, S-binap, and you can use either R or S-binap depending on which enantiomer you want. These are the structures of R and S-binap, and both are commercially available. Hydrogenolysis is commonly used to deprotect a benzyl ether to reveal the free alcohol, and notice that in this case you can selectively deprotect benzyl ethers over aliphatic ethers like methyl ethers. Now let's look at desulfurization with Raney nickel. Raney nickel is nickel saturated with hydrogen, and it's stored in water. It ignites if it's dry. It is great for converting carbon-sulfur bonds and reducing them to carbon-hydrogen bonds. So for example, in this case, we've removed both carbon-sulfur bonds and reduced them to carbon-hydrogen bonds. We can also use Raney nickel to decarboxylate. So if we do a two-step synthesis, we can take a carbonyl, like a ketone or an aldehyde, convert it to the dithiene, and then reduce both carbon-sulfur bonds with Raney nickel to get just the alkane. And finally, let's look at a diimide reduction. This is diimide, and it's a very gentle reducing agent. It's prepared from azo dicarboxylates, and treating with acetic acid generates diimide. The mechanism of this reaction is fairly straightforward. You've got the alkene attack one of the hydrogens. This is going to then form nitrogen gas and complete delivery of hydrogen. And so you've got your reduced alkene and you've generated nitrogen gas. This is an example of a reduction that diimide can do. Notice that it can reduce the alkene without rupturing this weak oxygen-oxygen bond.